Establishing a Mars Communication Network by 2025, a comprehensive overview. Introduction. In the pursuit of expanding human presence in space, the establishment of a robust communication network between Earth and Mars is a critical goal. This initiative aims to ensure seamless connectivity between the two planets, particularly as we prepare for future crewed missions to Mars. This report outlines the strategic development of three core technologies backed by a projected investment of $500 million aimed at achieving this objective by 2025. Objective. The primary objective of this initiative is to create a reliable communication network that facilitates real-time data exchange between Earth and Mars. As humanity embarks on the ambitious journey of exploring and potentially colonizing Mars, effective communication will be crucial for mission success, safety, and scientific collaboration. Core technologies. 1. Low Earth orbit LEO satellites. The deployment of a constellation of low Earth orbit satellites is fundamental to achieving continuous and reliable communication with Mars. LEO satellites positioned at altitudes ranging from 180 to 2,000 kilometers can significantly reduce latency in data transmission due to their proximity to Earth. Benefits: enhanced data transfer rates, reduced communication delays, improved reliability for both robotic and human missions to Mars. Implementation steps: design and prototype development of LEO satellites, testing and validation of satellite communication systems, launch of initial satellites into orbit as part of a phased deployment strategy. 2. Interplanetary relay systems. To facilitate effective communication between Earth and Martian assets, e.g. rovers' habitats, interplanetary relay systems are essential. These systems will utilize relay satellites positioned in orbit around Mars, acting as intermediaries to optimize the flow of information. Benefits: real-time data sharing between Earth and Mars, reliable communication during critical mission operations, enhanced coordination among various Martian missions. Implementation steps: development of relay satellite prototypes, establishment of a communication protocol for data transfer, integration with ground control operations on Earth. 3. Advanced signal processing technology. As missions to Mars generate vast amounts of data, advanced signal processing technology will be vital for managing and interpreting this information. Improved algorithms will enhance the clarity, reliability, and efficiency of communications over the vast distances involved. Benefits: better noise reduction and signal clarity, efficient handling of high-volume data streams, enhanced ability to process scientific data from Mars missions. Implementation steps: research and development of advanced signal processing algorithms, testing of signal processing systems in simulated environments, integration with satellite and relay systems for operational use. Investment and timeline. The proposed investment of $500 million is targeted at developing these core technologies by 2025. This funding will be allocated across several phases of development, including research, prototyping, testing, and deployment. Timeline: 2023 – initial discussions and proposals regarding technological requirements. 2024 – development of LEO satellite prototypes and initial testing of interplanetary relay systems. 2025 – target completion year for the deployment of a functional Mars communication network. Common themes across sources. Focus on connectivity. The importance of reliable communication systems is universally acknowledged as a cornerstone for the success of Mars missions. The ability to communicate effectively is essential for both crewed and uncrewed missions. Investment as a catalyst. There is a consensus that significant financial backing is critical to drive technological advancements and infrastructure development. The $500 million investment is viewed as a necessary catalyst for progress. International collaboration, the potential for collaboration between space agencies, private companies, and academic institutions is frequently highlighted. Such partnerships can foster innovation and share the burden of costs associated with developing these technologies. Differences noted among sources. While there is general agreement on the need for a communication network, some sources prioritize specific technologies over others. For instance, certain discussions place greater emphasis on satellite systems while others focus on advancements in signal processing. Additionally, projections regarding the timeline for technology deployment may vary, with some sources suggesting even earlier implementation. Conclusion: establishing a Mars communication network by 2025 represents a significant technological challenge that requires concerted efforts across various sectors. The integration of advanced satellite systems, relay technologies, and improved signal processing will be crucial for sustaining communications with Mars. This initiative not only aims to enhance our current understanding of the Red Planet but also paves the way for future exploration and potential human habitation, marking a pivotal step in our journey into the cosmos. In summary, the successful establishment of this communication network will play a vital role in ensuring that humanity can continue its exploration of space, making significant strides towards becoming a multiplanetary species. 1. Low Earth orbit LEO satellites. While the deployment of LEO satellites is often touted as a means to enhance communication efficiency, it is counterintuitive to assume that merely increasing the number of satellites will significantly reduce latency. In practice, the effectiveness of LEO satellite constellations can be limited by factors such as orbital mechanics, satellite handover processes, and ground station capabilities. Simply adding more satellites may not directly correlate with improved communication speeds. 2. Interplanetary relay systems. The reliance on relay satellites positioned around Mars for communication may lead to unexpected delays due to the distance involved. A common assumption is that such a system could provide instantaneous communication. But the reality is that data packets still need to traverse significant distances, resulting in inherent delays, especially during periods when Mars is on the far side from Earth. 3. Advanced signal processing technology. While advancements in signal processing are critical, there is a paradox in the assumption that more sophisticated algorithms will automatically yield clearer communication. In reality, increased complexity in algorithms can introduce new challenges such as processing delays and increased power consumption, which may counteract the benefits of clearer signals. There is also the risk that advanced algorithms could misinterpret data, leading to potential errors in communication. 4. Investment in timeline. The expectation of a $500 million investment to achieve a fully functional Mars communication network by 2025 might oversimplify the challenges involved. Historical projects in space exploration often suffer from budget overruns and delays. The assumption that a set timeline can be adhered to ignores the unpredictability of technological development and testing, which is often fraught with unforeseen complications. 5. Common themes across sources. The consensus that reliable communication systems are essential for Mars missions is a standard assumption in aerospace discussions. However, the emphasis on international collaboration as a unifying theme can be misleading. While collaboration is beneficial, differing priorities and agendas among countries and organizations may inhibit effective cooperation, leading to fragmented efforts rather than a cohesive strategy. 6. Differences noted. The variation in technology prioritization between sources suggests a lack of consensus on the most effective approach to establishing a Mars communication network. While some might advocate for satellite systems, others emphasize signal processing improvements. This discrepancy indicates that there is no one-size-fits-all solution, and certain technologies may be more applicable in specific scenarios than previously thought. 7. Timeline of events. The projection of specific milestones such as initial testing in 2024 and completion in 2025 assumes a linear progression of development. This overlooks the iterative nature of technology development, which often requires multiple rounds of testing and refinement. The assumption that a straight path can be followed may lead to underestimating the time needed for troubleshooting and optimization. In summary, while the establishment of a Mars communication network is a laudable goal, many assumptions underlying the proposed technologies and timelines may not hold true under scrutiny. The complexities of space communication technological development and international collaboration present a landscape that is far less predictable than optimistic forecasts suggest. The report on establishing a Mars communication network by 2025 outlines critical technological advancements and investments necessary to facilitate seamless connectivity between Earth and Mars. While many aspects of this initiative are highlighted, several important details may be overlooked by the general audience, which could significantly impact the success of the project. Overlooked content and its significance. 1. International collaboration. The report emphasizes the need for international collaboration among various stakeholders, including space agencies, private companies, and academic institutions. While many may recognize the importance of funding, the strategic partnerships that emerge from international collaboration are equally crucial. Significance. Successful Mars missions may depend more on collaborative efforts than on individual capabilities. By pooling resources, expertise, and technology, international partnerships can foster innovative solutions to complex challenges. This collaborative spirit can also help mitigate the financial burden on any single entity, ensuring a more robust and diverse approach to the communication network. 2. Focus on LEO satellites. The use of low Earth orbit LEO satellites is identified as a core technology. However, the specifics of their deployment, including the potential for a large constellation and the associated logistical challenges, are often glossed over. Significance. The technical challenges of deploying and maintaining a constellation of LEO satellites, e.g., collision avoidance, orbital decay, and maintenance, are substantial. Failure to address these could lead to communication blackouts or degraded service, which would undermine the entire Mars mission. Understanding these challenges is vital for ensuring the success of the communication network. 3. Interplanetary relay systems. The report mentions interplanetary relay systems but does not elaborate on the challenges and technologies involved in creating a reliable relay network around Mars. Significance. Developing effective relay systems is essential for real-time data sharing and communication between Earth and Martian assets. The complexity of Mars' atmosphere, along with potential obstructions like Martian terrain, poses significant challenges. Overlooking the intricacies of establishing this relay could lead to missed opportunities in scientific exploration and hinder mission success. 4. Advanced signal processing technology. While the report touches on signal processing technology, it does not delve into the algorithms and machine learning applications that will be crucial for interpreting the vast amounts of data sent back from Mars. Significance. As the volume of data from Mars missions increases, advanced signal processing becomes critical. Efficient data management and analysis could enable quicker decision-making and operational responses. Neglecting this technology's development could result in bottlenecks that hamper mission objectives and scientific discovery. 5. Investment allocation. The proposed $500 million investment is crucial, but the report lacks detail on how these funds will be allocated among the various technologies and partnerships. Significance. Transparent allocation of funds is necessary to ensure that all technological areas receive adequate attention. Misallocation could lead to underfunded projects that may fail to meet essential milestones, jeopardizing the entire network's functionality and reliability. 6. Timeline and milestones. The timeline indicates a target completion year of 2025, but the report does not outline specific milestones or checkpoints along the way that could help gauge progress. Significance. Establishing clear milestones is essential for project management. They provide a framework for assessing whether the project is on track, facilitating timely interventions when issues arise. Without this clarity, risks of delays or failures may increase, affecting the overall mission. 7. Potential technological alternatives. The report focuses on specific technologies but does not discuss potential alternatives or backup plans if initial technologies face challenges. Significance: technological development is often unpredictable. Having alternative strategies in place can help mitigate risks and ensure that the project remains on course. A lack of contingency planning can lead to critical failures if initial plans do not pan out as expected. 8. Public engagement and communication. The report does not address the importance of public engagement in the Mars Communication Network project. Significance: engaging the public can foster support for funding and policy initiatives related to the project. Public interest can also drive innovation through crowdsourcing ideas and solutions. Failure to involve the public could result in a lack of societal backing for the necessary investment and political support. 9. Impact on future space missions. The report discusses the immediate goal of establishing a communication network with Mars but overlooks the potential long-term implications for future interplanetary missions. Significance: a successful Mars communication network could serve as a model for future missions to other planets or celestial bodies. The technologies and strategies developed can influence the broader field of space exploration, enhancing humanity's ability to communicate across vast distances in space. Conclusion: the establishment of a Mars communication network by 2025 is a monumental undertaking that could redefine space exploration. However, to achieve success, it is essential to pay attention to the overlooked details in the report. Fostering international collaboration, addressing technological challenges, ensuring transparent funding allocation, and engaging the public are critical steps that will significantly influence the project's outcome. By focusing not only on the technologies themselves but also on the collaborative and operational frameworks surrounding them, stakeholders can better ensure the success of this ambitious endeavor. 1. Core technologies for Mars Communication Network. The foundation of establishing a Mars communication network by 2025 hinges on three pivotal technologies: low Earth orbit LEO satellites, interplanetary relay systems, and advanced signal processing technology. These technologies are essential for ensuring continuous and reliable communication between Earth and Mars. Addressing the inherent challenges of long-distance transmissions. LEO satellites will help reduce latency and improve data transfer rates, while relay systems will facilitate communication among Martian assets such as rovers and habitats. Furthermore, advanced signal processing algorithms will enhance the clarity and reliability of data across vast distances, which is critical for mission success. 2. Investment and economic viability. The projected investment of $500 million is a crucial aspect of this initiative, underscoring the economic commitment needed to develop the necessary infrastructure and technologies. This funding is not just a financial figure. It reflects the seriousness of the endeavor and the recognition that substantial backing is required to spur technological advancements. With the potential for crewed missions to Mars on the horizon, this investment represents not only a financial outlay but also a strategic move to ensure that the United States or collaborating nations maintains a leadership position in space exploration. 3. International collaboration. The discussions surrounding the establishment of a Mars communication network highlight the potential for international collaboration among space agencies, private companies, and academic institutions. Such partnerships can foster innovation, share costs, and pool resources, which is especially important given the high stakes and costs associated with space exploration. Collaboration can lead to shared technological advancements, increase the pool of expertise, and ensure that various stakeholders contribute to and benefit from the outcomes of Mars exploration initiatives. 4. Impact on future Mars missions. The establishment of a robust communication network by 2025 is not merely a technical upgrade, it has far-reaching implications for the future of Mars exploration. A seamless Earth-Mars connectivity will enable real-time data sharing, enhance remote operations of Martian missions, and support the establishment of a sustained human presence on Mars. The improvements in communication can facilitate better decision-making, allow for more sophisticated scientific experiments, and ultimately contribute to the success of future crewed missions. Thus, the development of this communication network is a critical step towards human colonization and deeper exploration of the Red Planet. 1. The Apollo Program 1961–1972. The Apollo program was a monumental effort by NASA to land humans on the Moon and ensure their safe return to Earth. The program involved significant technological advancements, including the development of the Saturn V rocket, the lunar module, and various communication systems that allowed for real-time data transmission between Earth and the lunar surface. The total cost of the Apollo program was approximately $25 billion, equivalent to over $150 billion today. Underscoring the need for substantial investment in technology and infrastructure to achieve ambitious space exploration goals. 2. The International Space Station ISS 1998–present. The ISS represents a collaborative effort among multiple nations, including the United States, Russia, Europe, Japan, and Canada, to create a permanent human presence in low Earth orbit. The project involved the development of numerous technologies such as advanced life support systems, robotics for assembly and maintenance, and enhanced communication capabilities. The ISS has received billions of dollars in investment over its lifespan, emphasizing the critical role of international collaboration and technological innovation in sustaining long-term space missions. 3. Mars Exploration Program 2000–present. NASA's Mars Exploration Program has seen the deployment of multiple rovers and orbiters such as Spirit, Opportunity, Curiosity, and Perseverance. Each mission has relied on advanced communication technologies to send data back to Earth. The program has involved significant investments in satellite systems for data relay, surface communications, and signal processing technologies to handle the challenges posed by the vast distances and variable conditions of Mars. Notably, the Mars Relay Network, which consists of orbiters that help transmit data from surface missions to Earth, highlights the importance of establishing robust communication networks for future exploration. The establishment of a Mars communication network by 2025 hinges on the development of 3 pivotal technologies and a projected investment of $500 million. This ambitious goal aims to facilitate seamless Earth-Mars connectivity, critical for future Mars exploration and potential human habitation. Here we present predictions for the future based on current technological trends and investment strategies. Core technologies and their future impact. 1. Low Earth orbit LEO satellites. Prediction: by 2025. A constellation of LEO satellites will be operational, enabling continuous and low-latency communication with Mars. This network will drastically reduce the time required for data transmission, which currently experiences delays of several minutes due to the vast distance. Future outlook: the success of LEO satellites for Mars communication will pave the way for advancements in satellite technology, leading to reduced costs and increased efficiency. Additionally, this infrastructure could be repurposed for other interplanetary missions, enhancing the overall capabilities of space communication networks. 2. Interplanetary relay systems. Prediction: the implementation of interplanetary relay systems, including satellites orbiting Mars, will become operational by 2025. These systems will facilitate real-time data sharing between Earth and Martian assets like rovers and habitats, enhancing mission efficiency and safety. Future outlook: as these relay systems become more sophisticated, they will enable more complex missions with multiple assets operating simultaneously on Mars. This capability will support advanced scientific research and exploration, making Martian missions more collaborative and effective. The technology may also inspire innovations in terrestrial communication systems. 3. Advanced signal processing technology. Prediction: by 2025, advancements in signal processing algorithms will enable the handling and interpretation of large volumes of data transmitted from Mars. Enhanced clarity and reliability in communications will be a hallmark of successful missions. Future outlook. The improvements in signal processing will not only benefit Mars missions but will also have applications in Earth-based communications, particularly in areas requiring high data fidelity such as telemedicine, remote sensing, and urban planning. These advancements could lead to breakthroughs in machine learning and artificial intelligence, creating more autonomous systems capable of processing complex data streams. Investment and collaborative strategies. Investment. The proposed $500 million investment will catalyze the development of these technologies. This funding will not only support research and development but also foster partnerships between governments, private companies, and academic institutions. Future outlook. As the technologies mature, we anticipate an increase in investment from both public and private sectors driven by the commercial potential of space exploration and the demand for advanced communication technologies. Additionally, international collaborations will become more common, with countries pooling resources and expertise to tackle the challenges of space exploration. Broader implications for space exploration. Human presence on Mars. The establishment of a robust communication network will facilitate future crewed missions, making it feasible to establish a sustained human presence on Mars. This will not only serve scientific objectives but also inspire public interest and investment in space exploration. Interplanetary infrastructure. Successful deployment of communication networks will serve as a blueprint for future interplanetary infrastructure. The technologies developed for Mars could be adapted for other celestial bodies such as the Moon or asteroids, supporting a more extensive exploration program across the solar system. Commercial opportunities. As the technologies and infrastructure develop, we can expect a surge in commercial opportunities related to space communications, satellite manufacturing, and data management services. This potential will attract a diverse range of investors and entrepreneurs, further enriching the space economy. Conclusion. The establishment of a Mars communication network by 2025 is not just a technological challenge, it represents a significant step toward humanity's future in space. The successful implementation of LEO satellites, interplanetary relay systems, and advanced signal processing technologies will not only enhance our ability to communicate with Mars but will also drive advancements in various fields, paving the way for a new era of exploration and innovation. The predictions outlined above suggest a future where interplanetary communication is robust, reliable, and transformative, ultimately supporting humanity's quest to explore and understand our place in the universe.